And now in this lecture, we'll answer two questions. In the first question, we will find out the area of this green shape using two different methods. And in the second question, we will find out the area of this circle that intersects with this right triangle ACP. So we start with the first question. In the drawing, we have quarter circle AOB. We know that OB equals to 2 units in its length. 97 AD equals to 97 DO. This is angle DCB. This is right angle, and our task is to find out the area of this green shape. The green shape is actually the green right triangle DCB. So we have to find out the area of this green right triangle DCB. So first of all, it is given us a question that AOB is a quarter circle, and therefore this is a right angle. Angle AOB is a right angle. And because of the fact that AOB is a quarter circle, OB is the radius, that is 2. AD is also, AO is also the radius. So AO equals to OB, the above the under of the quarter circle, is equals to 2. So AO is also the radius of this quarter circle, that equals to 2 units in its length. AO equals to 2. Point D is the midpoint of the radius AO. Why? Because at point D, the radius has been bisected into two halves. The first half is AD, and it is of course equal to the second half of the radius, that is DO. So the radius of this quarter circle, when we find the radius of this quarter circle is R, so R equals to 2. And at point D, the radius AO is bisected into two halves. So AO has been bisected into two halves, so each half must be equal to AO over 2. So the first half is AD, and it is of course equal to the second half of the radius DO, that is, and it is equal to the second half of the radius, that is DO. So at point D, the radius AO has been bisected into two halves. Each half must be also equal to AO over 2. So the first half is AD, and it is of course equal to the second half, that is DO. AO is 2, so AO over 2 is 2 over 2, that is 1. So in total, we found out that AD equals to DO equals to 1. AD equals to 1. That is the first half of the radius AO, and it is of course equals to the second half of the radius AO, that is DO, that is also 1. So this is triangle DOB, that is a right triangle. So in the next step, we will implement the Pythagoras theorem on this right triangle DOB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle DOB, here by PT is the ratio for Pythagoras theorem. So in this right triangle DOB, according to the Pythagoras theorem, dB squared, that is the square of the hypotenuse, equals to DO square plus OB square. And again, in this I tried D or B according to the Pythagoras theorem. The following equation is true. That dB squared, that is the square of the hypotenuse, equals to D all squared plus OB squared. dB is the missing side, so wherever it is, so it is dB squared equals to D all squared. DO is 1, so D all squared is 1 squared, that is 1. Plus OB squared. OB is 2, so OB squared is 2 squared, that is 4. So in total, we have found that dB squared equals to 1 plus 4, that is 5, so dB squared equals to 5. Here we take out all of this equation, and finally get the depth of the hypotenuse dB is equal to the square root of 5 units. This is the hypotenuse dB of this side and DOB, and it is equals to the square root of 5 units in its length. In the next step, we will do a construction, that is to say, we will complete this quarter circle to a circle So completed this concentric circle to a circle, and we'll extend the radius BO by a straight line until it touches the circle. And we define the touching point of the extended radius BO with this circle. This point is point P. When we extend a straight line by straight line, the result is a straight line. So PB is a straight line that touches the circle and those 2 points P and B. Therefore, PB is a chord that passes through the center of the circle, that is to say from point O. And we know that any chord that passes through the center of the circle must be the diameter of the circle. So write down that PB is the diameter of this circle, because it passes from point O, that is the center of the circle. PB is the diameter of this circle. In the next step, we will extend the radius AO by a straight line until it touches the circle. And we define the touching point of the extended radius AO with this circle. This point is point Q. Point O is the center of this circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle, that equals to 2. Likewise, point O is the center of this circle, point P is the point of the circle itself, therefore OP is also the radius of this circle. That is equals to 2 units in its length. In the next step, we will extend side CD or line segment CD by side line until it touches the circle. But the question is where the extended side CD will touch the circle. We will assume that the extended side CD will not touch the circle at point P, but at other points, for example, we will assume that the extended side CD will touch the circle at this point that we define as point N. So in the drawing we have peripheral angle BCN. This is peripheral angle BCN. That's equals to 90 degrees inside. But peripheral angle BCN subtend on chord BN. Again, peripheral angle BCN, that is equals to 90 degrees inside, subtend on chord BN. Chord BN is definitely not the diameter of the circle. When put this is chord BN, peripheral angle BCN subtend on chord BN. Chord BN doesn't pass from point O, that is the center of the circle, and we know that any chord that doesn't pass from the center of the circle cannot be the diameter. So we have peripheral angle BCN that is equal to 90 degrees inside, and still it doesn't subtend on the diameter of the circle, and therefore it is a contradiction to rule 5. So basically on rule 5, according to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. So here we have peripheral angle MAN, that is the right angle, it's equal to 90 degrees in size, and it subtends on chord MAN, that is the diameter of the circle. So according to this rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. But here we have peripheral angle BCN that is equal to 90 degrees in size, and it still doesn't subtend on the diameter of the circle because NB is definitely not the diameter of the circle. So due to the contradiction to rule 5, we cancel this solution, this option. It means that the extended side CD cannot touch the circle at point N due to contradiction to rule 5. In the next step, we will assume that the extended side CD will touch the circle at this point. We define the touching point, this point is M. So we have peripheral angle BCM. This is peripheral angle BCM. This is equal to 90 degrees inside, and it subtends on chord BM. Again, peripheral angle BCM, this is equal to 90 degrees inside, subtends on chord BM. This is chord BM. Chord BM is definitely not the diameter of the circle because of the fact that it doesn't pass for point O, that is the center of this circle. And because of the fact that chord BM is not the diameter of the circle, we have contradiction to rule 5 because we have peripheral angle BCM that is equal to 90 degrees inside, and still it doesn't subtend on the diameter of the circle. So therefore it is a contradiction to rule 5. Therefore, can conclude from it that the extended side CD will not touch the circle at point M. And therefore, we will conclude that the extended side CD will touch the circle at point P and not in any other point. Otherwise, we will have a contradiction to rule 5. So, we have here, this is triangle BCP, that equals to 90 degrees inside, and it's obtained on chord PB, that is the diameter of the circle. Why PB is the diameter of the circle? Because of the fact that it passes from point O, that is the center of the circle. So, in conclusion, we can say that the extended side CD will touch the circle at point B and not in any other point. Okay, so in the next step, we focus on this point O. PB is the diameter of this circle. So PB is the diameter of the circle, it is absolutely a straight line. So if you focus on the upper side of the straight line PB at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line PB at point O? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will implement the Pythagoras theorem on this right rail PDO. PO is 2, DO is 1, so the opponent must be equal to 5 because we already found out that here the same triangle we have OB is 2, DO is 1, and therefore the opponent is called root of 5. So it is the same triangle actually. 2, 1, and then the opponent must be equal to the square root of 5, according to the Pythagoras theorem. So in the next step, we will implement rule 24 in our drawing. So I repeat quickly on rule 24. Rule 24 is true in any circle, so in any circle, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. In the drawing of a circle, this is chord AB that intersects with chord CD at point O. So in this drawing, whenever you have two chords that intersect with each other in a circle, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement rule 24 in our drawing. Why? Because in our drawing, we have chord AQ intersects with chord CP at point D. Again, chord AQ intersects with chord CP at point D. So I write it now. chord AQ intersects with chord CP at point D. The intersection point occurs at point D. And again, in our original drawing, chord AQ intersects with chord CP at point D. So all the requirements of rule 24 are satisfied, and therefore we can implement here rule 24. According to rule 24, the following equation is true. That AD times DQ equals to CD times DP. Again, according to rule 24, the following equation is true. That AD times DQ equals to CD times DP. AD is 1 times DQ. DQ in total equals to 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so we leave it as it is. Times dp. dp equals to the square root of 5 units in its length. So in total, according to rule 24, we have found out that 1 times 3 equals to CD times square root of 5. 1 times 3 is 3, so 3 equals to CD times square root of 5. Here we divide the equation by square root of 5, and we get that CD equals to 3 over square root of 5 units in its length. This is the missing side CD. This equals to 3 over square root of 5 units in its length. In the next step, we will implement the Pythagoras theorem on this right triangle DCB. Here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in this right triangle DCB, dB square, that is the square of the hypotenuse, equals to DC square plus CB square. And again, in this right triangle DCB, according to the Pythagoras theorem, the following equation is true. The dB square, that is the square of the hypotenuse, equals to DC square plus CB square. dB is square root of 5, and therefore dB square is square root of 5 squared, that is 5. And it is equals to DC square. DC equals to 3 over square root of 5, and therefore DC square equals to 3 over square root of 5 squared, that is 9/5. Plus CB square. CB is the missing side, so we leave it as it is. So in total, according to the Pythagoras theorem, we found out that 5 equals to 9/5 plus CB square. Here we multiply 5 by 5 and then we divide it by 5 in order to overcome a factor of this number. And when you get that 5 times 5 is 25, divided by 5. We multiply it by 5 and then we divide it by 5, so we change nothing. So 25 over 5 equals to 9 fifths minus 3b squared. Here we subtract 9 fifths from this equation and finally we get that 25 fifths minus 9 fifths equals to 16 fifths equals to CB squared. Here we take out all those equations and finally we get that the missing side CB is equal to the square root of 16 is 4 over square root of 5. But again, in total, if you found out that the missing side CB, or the general time DCB, is equal to 4 over square root of 5 units in its length. So this is the missing side CB, is equal to 4 over square root of 5 units in its length. Our test is to find out the area of this green shape. The green shape is actually the green rectangle DCB. Repeat again. Our task is to find out the area of this green shape, and the green shape is the green rectangle DCB. The area of this green rectangle DCB equals to the base DC times the height CB over 2. And again, the area of this green rectangle DCB equals to the base DC times the height CB over 2. DC equals to 3 over square root of 5 times CB. CB equals to 4 over square root of 5 divided by 2. So in total, if you found out that the area that we are looking for in this question, that is the area of this green shape, that is the area of this green rectangle DCB, is equal to 3 over square root of 5 times 4 over square root of 5 divided by 2. 3 times 4 is 12 over square root of 5 times square root of 5 is 5 over 2. So here we move to the numerator and we get that this expression in total equals to 12 over 5 times 2, that actually equals to 12 tenths. Or in terms of numbers, it is equal to 1.2 square meters in size. So again, if you found out that the area that we are looking for this question, that is the area of this green shape, in total it is equal to 1.2 square meters in size. So we finish with the first method. In the next step I present to you how to find out the area of this green shape according to the second method. We know that AO equals to BO, above the radii of the quarter circle, is equals to 2. At point D, the radius AO has been bisected into 2 halves, so each half equals to 1. The first half of the radius AD is 1, the second half of the radius DO is also equals to 1. Okay. AOB is a quarter circle, and therefore this is a right angle. In the next step, we will complete this quarter circle to a semicircle. And we'll extend the reduce BO by third line until it touches the semicircle. When you find the touching point of the third reduce BO with this semicircle, this point is point P, as we did in the first method. PB is of course the diameter of this semicircle. It is true in any semicircle. I can give another reason why PB is the diameter of the circle, because we extended the reduced BO by third line, and the result, when we extend the third line by third line, the result must be a third line. So PB is a third line. PB is the third line that touches the semicircle at 2 points, P and B. Therefore, PB is a chord. PB is a chord that passes through point O, that is the center of the semicircle, and we know that any chord that passes through the center of the semicircle or a circle must be the diameter of the circle or semicircle. So PB is the diameter of this semicircle. As I already mentioned in the first method, when you extend line 7 CD, it must touch the semicircle or a circle at point B and not in any other point. Otherwise, you will have contradiction to rule 5. In order to avoid the contradiction to rule 5, we must conclude that the extended side CD must touch the semicircle at point P. Point O is the center of this semicircle, point P is the point of the semicircle itself, therefore OP is the radius of this semicircle, is equals to 2 units in its length. Here we have, as already mentioned, explained the first method. According to rule 3, this missing angle equals to 90 degrees in its size. Why? Because PB is a straight line, it's a diameter. If we focus on the upper side of the straight line PB at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have the upper side of PB at point O, we have this angle that is the right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees. Therefore this missing angle must be equal to 90 degrees in its size, according to rule 3. So this is the triangle POD. This right triangle is only found out in the first method. We have PO is 2, is the radius. DO is 1, therefore the opponent must be equal to the square root of 5 units in its term according to the Pythagoras theorem. I'll not repeat on the same thing that we already done in the first method. Okay. In the next step, we'll focus on this right triangle OPD. On this right triangle OPD, we'll define this angle DPO as alpha. So in this right triangle POD, this angle equals to alpha, this angle equals to 90 degrees, and therefore this one, this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in this big right triangle PCB, this angle equals to alpha. This angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees also for the same reason. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. So this angle must be equal to 90 degrees minus alpha. Actually, it is very easy to see that this is the right triangle PDO is similar to this big right triangle PCB. So why the right triangle PDO is similar to this big right triangle PCB? First of all, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself. It's a common angle that belongs to both triangles. Angle alpha definitely belongs to this right triangle POD, and angle alpha is definitely belongs to the big right triangle PCB. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. Likewise, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So actually, we found out in total that all the three angles of this small right triangle PDO are corresponding equal to all the three angles of this big right triangle PCB. And therefore, those two right triangles can be similar to each other according to angle similarity rule. So I write it down. First, we found out that this is the small right triangle PDO, and it's similar. This is the sign of similar to this big right triangle PCB according to angle similarity rule. Repeat again, we found out that the small right triangle POD is similar to the big right triangle PCB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side PD of this small right triangle PDO over side PB of this big right triangle PBC, PD over PB equals to side DO of this small right triangle POD over side CB of this big right triangle PCB, and it is also equals to side PO of this small right triangle POD over side PC of this big right triangle PCB. Repeat again, from the fact that this is the small right triangle PDO is similar to this big right triangle PCB, we will derive that the following relationship exists between their sides. We will derive that side PD of the small right triangle POD over side PB of the big right triangle PCB is equal to side DO of the small right triangle PDO over side CB of the big right triangle PCB, and it is also equal to side PO of the small right triangle PDO over side PC of the big right triangle PCB. This is side PD. This is equals to the square root of 5 units over PB. PB in total equals to 2 plus 2, that is 4. And it is equals to DO. DO equals to 1 over CB. CB is the missing side, so we limit as it is. And it is also equals to PO. PO equals to 2 over PC. PC in total equals to the square root of 5 plus DC. Again, PC in total equals to the square root of 5 plus DC. So in total we shall find out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. So those two sides of the equation are equal to each other. So we will get equation 1 from those two sides that are equal to each other. So according to equation 1, we will get that square root of 5 over 4 equals to 1 over CB. Here we will cross multiply the equation 1, and we get that according to equation 1, square root of 5 times CB equals to 4. Here we will divide this equation 1 by square root of 5, and finally get that according to this equation 1, CB equals to 4 over square root of 5 units in its length. So if you found out that the missing side CB of the granite DSB is equal to 4 over square root of 5 units in its length. This is side CB. This is equals to 4 over square root of 5 units in its length. Those two sides of the equation are also equal to each other. So we get equation 2 from those two sides that are equal to each other. According to equation 2, we get that square root of 5 over 4 equals to 2 over square root of 5 plus DC. And again, according to equation 2, we can find out that square root of 5 over 4 equals to 2 over square root of 5 plus DC. Here we will cross multiply the equation 2, and get that according to this equation 2, 2 times 4 is 8. So 8 equals to square root of 5 times square root of 5 plus DC. And again, according to equation 2, we actually found out that eight equals to the square root of 5 times square root of 5 plus DC. Here we will open the brackets on this side of this equation 2, and we get that according to this equation 2, 8 equals to square root of 5 times square root of 5 is 5, plus square root of 5 times DC. So in total we found out that 8 equals to 5 plus square root of 5 times DC. Here we will subtract 5 from this equation 2, and finally we get that according to this equation 2, 8 plus 5 is 3, equals to square root of 5 times DC. Here we will divide this equation 2 by square root of 5, and finally we get that according to this equation 2, DC equals to 3 over square root of 5 units in its length. So actually, this is the missing side DC. This equals to 3 over square root of 5 units in its length. our task is to find out the area of this green shape. The green shape is actually the area of, is the right green triangle DCB. We already done it in the first method, but I repeat on it anyway. Again, the area of this green shape is the area of this green triangle DCB. And the area of this green triangle DCB equals to the base DC times the height CB over 2. Okay, again, the area of this green triangle DCB, that is the area of the green shape also, it is equals to the base DC times the height CB over 2. DC equals to 3 over square root of 5 times CB. CB equals to 4 over square root of 5 divided by 2. So in total, if you found out that the area of the green shape equals to 3 over square root of 5 times 4 over square root of 5 divided by 2. Here 3 times 4 is 12, over square root of 5 times square root of 5 is 5 over 2. So we have 12 over 5. We will move 2 to the denominator. So in total this expression equals to 12 over 5 times 2, that is 12 over 10. 12 over 10 is 1.2. So if you found out that the area of the green shape in both methods, it is equals to 1.2 square units in size. Okay, again, in both methods, we found out that the area that we are looking for this question, that is the area of this green shape, in total it is equals to 1.2 square units in size. So we finish with the first question. In the next step, I present to you the second question and solve the second question of this lecture. In the second question, our task is to find out the area of this circle. So in the drawing we have a circle. This circle intersects with this right triangle ACP. So this is angle ACP, this is right angle. We know that this is line segment BC, this is equals to 1 unit in its length. This is side CP, this is equals to 4 units in its length. Again, our task is to find out the area of this circle. So here we can implement rule 2 in our drawing. I click quickly on rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing we have a circle. This is the common standpoint point P. From this common standpoint point P, we have two tangents to this circle, tangent PA, tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Well, in our drawing, this is the common standpoint point P. From this common standpoint point P, actually it is given us the question that PA and PB are two tangents to the circle. From the common standpoint point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. Hit again. Now original drawing, we have only to rule 2. Tangent PA equals to tangent PB in its length. PB in total equals to 4 plus 1, that is 5. So I can write here that PB equals to 5. And from this equation, PA equals to PB equals to 5. We will derive that PA must be also equal to 5 units in its length. This is tangent PA that is equals to 5 units in its length. So this to rule 2. So in the next step we'll focus on this right triangle, right big triangle ACP. And we will implement the Pythagoras theorem on this right big triangle ACP. So here by PT is a preparation for Pythagoras theorem. This right triangle ACP according to the Pythagoras theorem, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. And again, this right triangle ACP according to the Pythagoras theorem, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25. And it is equals to AC squared. AC is the missing side, so we leave it as it is. It is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total, we found out that 25 equals to AC squared plus 16. Here we subtract 16 from this equation and find again that 25 minus 16 is 9. So 9 equals to AC squared. Here we'll take a root out of the equation and find again that the missing side AC is equal to the square root of 9, that is 3. So AC equals to 3 units in its length. This is the missing side AC, is equals to 3 units in its length. In the next step, we will define the center of this circle. This point is point O. And remind you that PB is a tangent to this circle at point B. And we will join points O and B together by straight line. Point O is the center of this circle, point B is a point on the circle itself, therefore OB is the radius of this circle. We will define the radius of this circle as x, so OB equals to x. So here we can implement rule 1, because the radius OB is equals to x, the radius OB is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. In the next step, PB is a tangent to this circle. So PB is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line P8 point C, here the sum of the areas must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the areas on one side of the straight line is equal to 180 degrees. So which areas we have at the upper side of the straight line P8 point C? We have this angle, the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do a construction, that is to say, from point O, that is the center of this circle, we will draw perpendicular on AC. Again, from point O, we will draw perpendicular on AC. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point M. By doing this construction, we create a deal quadrilateral CBOM. Inside this quadrilateral CBOM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle in total must be equal to 360 degrees. According to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in size. So inside quadrilateral OMCB we have 4 right angles, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in a rectangle OMCB, side BC must be equal to the opposite side OM, but BC is 1, therefore OM must be also equal to 1 unit in its length. Likewise, according to the sum rule, in the same rectangle AOM, in the same rectangle OMCB, side OB must be equal to the opposite side MC. But OM is x, it is the radius of the circle, and therefore MC must be also equal to x units in its length. What is the length of AM? From the drawing, it is very easy to see that AM in total equals to AC minus MC. So, if you know that the missing side AM equals to AC minus MC. So the missing side AM, this is the missing side AM, that in total is equals to AC, AC is 3, minus MC, MC is x. So in total AM equals to 3 minus x units in its length. This is the missing 97 AM, this is equals to 3 minus x units in its length. In the next step, we will join points O and A together by straight line. Point O is the center of this circle, point A is the point of the circle itself, therefore OA is the radius of this circle, is equals to x. In the next step, we will implement the Pythagoras theorem on this right triangle AOM. So in the green right triangle AOM, here by PT is evaluation for Pythagoras theorem. So in this green right triangle AOM, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AM squared plus OM squared. And again, in this given right triangle AOM, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AM squared plus OM squared. AO is x, therefore AO squared is x squared. And it is equals to AM squared. AM is 3 minus x, and therefore AM squared is 3 minus x squared. Plus OM squared. OM is 1, therefore OM squared is 1 squared, that is 1. So in total, we should now know that x squared equals to 3 minus x squared plus 1. So here we will open the brackets on this side of this equation and find that x squared equals to 3 minus x squared equals to 3 squared, that is 9, plus x squared minus 2 times 3 times x, that is minus 6x plus 1. Here we have x squared on both sides of the equation, so x squared gets cancelled. After we cancelled x squared, on this side of the equation we left with nothing, that is to say 0, while on the other side of the equation we have 9 plus 1, that is 10, minus 6x. So in total, we found out that 0 equals to 10 minus 6x. Here we add 6x to this equation, and get that 0 plus 6x is 6x, equals to 10. So now we found out that 6x equals to 10. X is the radius of the circle. That is the radius that we are looking for this question. So here we divide this equation by 2. And finally get that 6x over 2 is 3x. And it is equals to 10 over 2, that is 5. So 3x equals to 5. Here we divide this equation by 3. And finally get that x, that is the radius of the circle, is equal to 5 thirds. X equals to 5 thirds. The radius of this circle, we are looking for the area of this circle, and the radius of this circle, x equals to 5 thirds. And therefore the area of this circle must be equal to pi x squared. And again, the area that we are looking for in this question, that is the area of this circle. In total, it must be equal to pi times the radius squared. That is to say, it is pi times x squared. So it is pi times x squared. X is 5 thirds, and therefore x squared is 5 thirds squared. So it is pi times 5 thirds squared. 5 thirds squared equals to 5 squared, that is 25. Over 3 squared, that is 9. So in total, we found out that the area that we are looking for in this question, that is the area of this circle, it is equal to either 25 pi over 9 square units in size, or in terms of numbers, it is equal to 8.73 square units in size. If it again, if you found out that the answer to the question is that the area of this circle, that is the area that we are looking for in this question, it is equal to either 25 pi over 9 square units in size, or in terms of numbers, the area of this circle equals to 8.73 square units in size. So we finish the second question. In the next step on some of the lecture, we'll start with the repetition of the first question, both methods, then we repeat on the solution of this second question. So we start with the first question. In the first question, our task was to find out the area of this green shape. So, in in the drawing we have a quarter circle, AOB is a quarter circle. It is given us the question that line 7 AD equals to line 7 DO. This is the line 7 OB, side or side OB. This is equals to 2 units in its length. This is angle BCD, this is the right angle. Again, our task is to find out the area of this green shape. The green shape, it is actually the right green triangle DCB. So we have to find out the area of this green right triangle DCB. We found out the area of this green right triangle by using two different methods. So we start with the first method. So AOB is a quarter circle and therefore this is the right angle. The AOB, here we have OB equals to OA. The above the area of the quarter circle. OB is 2, therefore the radius OA also equals to 2. At point D, the radius AO is being bisected to 2 halves. So the first half AD equals to the second half DO. And each half must be, of course, equals to the radius over 2. That is to say, it is 2 over 2, that is 1. So the first half AD is 1, and the second half of the radius AO is also 1. Okay. So in the next step, we implemented the Pythagoras theorem on this right triangle BOD. Only to the Pythagoras theorem in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle BOD, again dB squared, that is the square of the hypotenuse, equals to DO squared plus OB squared. So in the right triangle DOB, according to the Pythagoras theorem, dB squared, that is the square of the hypotenuse, equals to DO squared plus OB squared. dB is the missing side, so it is dB squared equals to DO squared. DO is 1, therefore DO squared is 1 squared, it is 1, plus OB squared. OB is 2, therefore OB squared is 2 squared, it is 4. So in total, we should found out that dB squared equals to 1 plus 4, that is 5. So dB squared equals to 5. Here we took out of the equation and we found out that the missing hypotenuse dB is equals to the square root of 5 units in its length. This is the hypotenuse dB. This is equals to the square root of 5 units in its length. In the next step, we completed this quarter circle to a circle. Then we extended the radius BO by side line until it touches the circle. We define the touching point of the extended radius BO with this circle. This point is point P. When you extend the side line by side line, the result BP is also a side line. So BP is a side line that touches the circle at 2 points, P and B. Therefore, BP is a chord. BP is a chord that passes through point O, that is the center of the circle. And we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, PB is the diameter of the circle. Point O is the center of this circle. Point P is the point of the circle itself. Therefore, OP is the radius of this circle. Radius of this circle is equals to 2. Then we extended the radius AO by side line until it touches the circle. We define the touching point of the extended radius AO with this circle. This point is point Q. So point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle, it is equals to 2. And actually AQ is the diameter of the circle because it passes from point O, that is the center of the circle. In the next step, we implemented the Pythagoras theorem on this right triangle DOB. OP equals to 2, DO equals to 2. It is exactly the same triangle, and here we only found out that in this triangle the hypotenuse DB is equal to 5, therefore this the same line triangle, the hypotenuse DP must be also equal to the square root of 5 units in its length. In the next step, we extended line 7 CD by side line until it touches the circle. And the question is where the extended line 7 CD will touch the circle. Actually, I explained to you that the extended side CD must touch the circle at point P and not in any other point, otherwise we will have contradiction to rule 5. For example, if the extended side CD will touch the circle at point N, then we will have periangle BCN is equal to 90 degrees in size, and it still doesn't subtend on the diameter of the circle because Bn is definitely not the diameter of the circle because it doesn't pass through point O, that is the center of the circle. So due to the contradiction to rule 5, we conclude that the extended side CD cannot touch the circle at point N. Then we assume that the extended side CD will touch the circle at this point, point M. Then we will have periangle BCM. This goes to 90 degrees inside and subtend of chord VM. Chord VM is definitely not the diameter of the circle because it doesn't pass through point O, that is the center of the circle. Again, we have contradiction to rule 5, and therefore we must conclude that the extended side CD will touch the circle at point P and not in another point due to the contradiction to rule 5. So we have here periangle BCP that is equal to 90 degrees inside. Periangle BCP subtend on chord PB, that is the diameter of the circle, exactly according to rule 5. Okay. So, I want to explain to you that this angle equals to 90 degrees inside according to all 3. So, because PB, the diameter is a straight line, if we focus on the upper side of the straight line PB at point O, here the sum of the angles must be equal to 180 degrees. So 90 degrees plus the missing angle in total must be equal to 180 degrees, therefore this missing angle must be equal to 90 degrees inside. So triangle PDO is a right triangle, and we implemented the Pythagoras theorem on this right triangle PDO. The hypotenuse of this right triangle must be equal to the square root of 5, exactly like this right triangle. Okay, and the next step, we implemented rule 24 in our drawing. Rule 24 is about two chords that intersect with each other in a circle. According to rule 24, if chord AB intersects with chord CD at point O, then the following equation is called AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So in the drawing circle, this is chord AB that intersects with chord CD at point O. Again, chord AB intersects with chord CD at point O. So in this drawing, the following equation is called that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement all 24 in our drawing. This is called AQ, so as I already mentioned before, AQ is the diameter of the circle. So we have chord AQ that intersects with chord CP at point D. Again, chord AQ intersects with chord CP at point D. Again, in our original drawing, we have chord AQ that intersects with chord chord CP at point D. So all the requirements of rule 24 are satisfied, and therefore we can implement here rule 24. According to rule 24, the following equation is called that AD times DQ equals to CD times DP. Again, AD times DQ equals to CD times DP. And again, according to rule 24, the following equation is called that AD times DQ equals to CD times DP. AD is 1 times DQ. DQ in total is 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so we leave this it is, times DQ. DQ is equal to 5. So in total, we found out that 1 times 3 equals to CD times square root of 5. 1 times 3 is 3, so 3 equals to CD times square root of 5. Here we divided this equation by square root of 5 and found out that the missing side CD is equal to 3 over square root of 5 units instead. This is the missing side CD that is equal to 3 over square root of 5 units in its length. In the next step, we implemented the Pythagoras theorem on this green right side DCB. According to the Pythagoras theorem, in this right triangle DCB, dB squared, that is the square of the hypotenuse, equals to CD squared plus CB squared. And again, in the right triangle DCB, dB squared, that is the square of the hypotenuse, equals to DC squared plus CB squared. dB equals to the square root of 5, and therefore dB squared square root of 5 squared, that is 5, and it is equals to DC squared. DC equals to 3 over square root of 5, and therefore DC squared is 3 over square root of 5 squared, that is 9 fifths, plus CB squared. CB is the missing sign, so we leave it as it is. So in total we found out that 5 equals to 9 fifths plus CB squared. Here we multiplied 5 by 5 and then we divided it by 5 in order to come a factor with this number. So we have 5 times 5 is 25 over 5. So 25 over 5 equals to 9 fifths plus CB squared. Here we subtract 9 fifths from the equation and find out that CB squared equals to 25 fifths minus 9 fifths is 16 fifths. So 16 fifths equals to CB squared. Here we took out of the equation and found out that the missing sign CB equals to the square root of 16, that is 4 over square root of 5. This is the missing sign CB, that is equals to 4 over square root of 5 units in its length. Our task is to find out the area of this green shape. The green shape is the right triangle DCB, so we have to find out the area of this green right triangle DCB. Okay, again, our task is to find out the area of the green shape, that is the area of the green right triangle DCB. The area of this green right triangle DCB equals to the base DC times the height CB over 2. And again, the area of the green right triangle DCB equals to the base DC times the height CB over 2. DC is 4 over square root of 5 times CB is 4 over square root of 5 divided by 2. 3 times 4 is 12. Square root of 5 times square root of 5 is 5 over 2. Here we move 2 to the denominator. So in total this expression equals to 12 over 5 times 2, that is 10. So in total the expression there of the green shape equals to 12 tenths, that is 1.2. So if you found out the area that you are looking for this question, that is the area of this green shape, in total it is equal to 1.2 square units in size. So we finish with the first method. The next step I presented to you how to find out the area of this green shape according to the second method. We know that OB equals to OA, above the radii of the quarter circle, that equals to 2. At point D, the radius of AO is been bisected into 2 halves, each half equals to 1, of course. So AD equals to 0 equals to 1. This is the right angle because of the fact that AOB is a quarter circle. So we completed this quarter circle to a semicircle. According to rule 3, as we only done in the first method, this angle equals to 90 degrees. Because BB is the diameter is absolute inside line, so if you focus on the upper side of the third line PB 8.0, with the sum of the x must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we extended side CD by side line until it touches the semicircle. We define the touching point of the extended side CD with this semicircle. This point is point P. I already explained in the first method that the extended side CD must touch the semicircle at point P and not in any other point due to the contradiction to rule 5. The only point that is extended side CD will touch the circle is point P and not any other point. And then we not have condition to rule 5 anymore because we have triangle BCP, that is a right angle, and it indeed subtend on PB, that is the diameter of this semicircle, exactly according to rule 5. So we implemented the Pythagoras theorem on this triangle PDO. In the first method we found out that the hypotenuse PD equals to the square root of 5. So in this triangle PDO, we define this angle OPD is alpha, so in the right triangle PDO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. 1 equals to 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees, that is the sum of negatives in the triangle. So this first missing angle must be equal to 90 degrees minus alpha. Likewise, in the big right triangle PCB, this angle equals to alpha, this angle equals to 90 degrees, according to what is given as the question. And therefore, this third missing angle, that is to say angle CBP, must be equal to 90 degrees minus alpha. According to the sum rule that states that the sum of the angles in a triangle is equal to 180 degrees. It is very easy to see that this is the right triangle PDO that is similar to the big right triangle PCB. So all those two right triangles are similar to each other. First of all, this is angle alpha, this is a common angle that belongs to both triangles. So we can find out that angle alpha equals to itself is a common angle that belongs to both triangles. Likewise, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So I shall prove that all the figures of this whole right triangle PDO correspond equal to all the figures of the big right triangle PCB. And therefore those two right triangles are similar to each other according to angle similarity rule. So if again I shall find out that the small right triangle PDO is similar, this is the sum of similar to the big right triangle PCB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive the following relationship exists between their sides. We derive that side PD of this small right triangle PDO or side PB of this big right triangle PCB is equal to side DO of this small right triangle PDO or side CB of this big right triangle PCB, and it is also equal to side PO of this small right triangle PDO or side PC of this big right triangle PCB. And again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between the sides. We derive that side PD of the small triangle or side PB of the big triangle equals to side DO of the small triangle or side CB of the big triangle, and it is also equal to side PO of the small triangle or side PC of the big triangle. PC is equal to 5, PB is 4, DO is 1, CB is the missing side, so it is. PO is 2, and PC in total, this is side PC in total is equal to the square root of 5 plus DC. Again, PC in total equals to the square root of 5 plus DC. So in total, if you found out that square root of 5 over 4, square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Those two sides of the equation are equal to each other. Therefore, we can do the equation 1 from those two sides. That is to say, square root of 5 over 4, square root of 5 over 4 equals to 1 over CB. Square root of 5 over 4 equals to 1 over CB. Here, of course, multiply the equation, if I found out that 4 equals to the square root of 5 times CB. Here we divided the equation by square root of 5 and finally found out that the missing side CB equals to 4 or square root of 5 units in its length. This is the missing side CB. This is equals to 4 over square root of 5 units in its length. Those two sides of the equation are also equal to each other, so we can do the equation 2 from those two sides that are equal to each other. According to equation 2, we shall find out that square root of 5 over 4 equals to 2 over square root of 5 plus DC. Again, according to equation 2, square root of 5 over 4 equals to 2 over square root of 5 plus DC. Here we can multiply this equation and find out that 2 times 4 is 8 equals to the square root of 5 times square root of 5 plus DC. Again, so that if you found out that so we cross multiply the equation, if we found out that 8 equals to the square root of 5 times square root of 5 plus DC. Here we open the brackets on this side of the equation 2, in total if you found out that 8 equals to the square root of 5 times square root of 5 is 5, and square root of 5 times DC is square root of 5 times DC. So in total, according to equation 2, if you found out that 8 equals to 5 plus square root of 5 times DC. Here we subtract 5 from this equation and found out that 8 times 5 is 3 equals to the square root of 5 times DC. Here we divided this equation by square root of 5 and finally found out that the missing side DC equals to 8 3 over square root of 5 units in its length. This is the units inside DC. This is equals to 3 over square root of 5 units in its length. Our test is to find out the area of this green shape. The green shape is the green right triangle DCB. The area of this, so total the area of the green shape is the area of the green right triangle DCB. And the area of this green right triangle DCB equals to the base DC times the height CB over 2. And again, the area of this green right triangle DCB in total is equals to the base DC times the height CB over 2. DC is 3 over square root of 5 times CB is 4 over square root of 5 divided by 2. 3 times 4 is 12. Square root of 5 times square root of 5 is 5 over 2. Here we move to the denominator. So this expression equals to 12 over 5 times 2, that is 10. So in total this expression equals to 12 tenths, that is 1.2. So in both methods, as you know that the area that we're working on this question, that is the area of this green shape, in total it is equal to 1.2 square units in size. So I finished to answer on the first question. In the next step, I repeat on the solution on the second question. On the second question, our task is to find out the area of this circle. So in the drawing circle, this circle intersects with this right triangle ACP. This is line 7BC, that is equals to 1 unit in its length. This is line 7CP, that is equals to 4 units in its length. This is again ACP, that is right again. Again, our task is to find out the area of this circle. We define the center of this circle, this point is point O. Then we focus on this common center point P. From the common center point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say PA equals to PB. According to rule 2, PA equals to PB. But it is given as a question that PB in total equals to 4 plus 1, that is 5. So we can iterate that PB equals to 5, and from this equation PA equals to PB equals to 5, we will derive that PA also equals to 5 units in its length. This is tangent PA, is equals to 5 units in its length. It is given as a question that PA and PB are tangent to this circle. So tangent PA equals to 5 units in its length. In the next step, we implemented the Pythagoras theorem on this right triangle ACP. According to the Pythagoras theorem, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. And again, this right triangle ACP, according to the Pythagoras theorem, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25. And it is equals to AC squared. AC is the missing side, so leave it as it is, plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total, if you found out that 25 equals to AC squared plus 16. Here we subtract 16 from this equation, and when we found out that AC squared equals to 25 from 16, that is 9. So AC squared equals to 9. Here we took out all those equations, and when we found out that the missing side AC equals to the square root of 9, that is 3. This is the missing side AC, that is equals to 3 units in its length. In the next step, as I mentioned before, we define the center of this circle. This point is point O. And Point B is the point of tendency of tangent PP in this circle, with this circle. The next step, we join points O and B together by straight line. Point O is the center of this circle, point B is the point of the circle itself, therefore OB is the radius of this circle. We define the radius of this circle as x, so OB equals to x. The radius of OB is equals to x, the radius of OB is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, the point of tendency, then tangent PB will be perpendicular to the radius PO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. This angle is right angle according to rule 3. PB is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line PB at point C, the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PB at point C? We have this angle that is right angle, plus this missing angle, the total the sum of those angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we did the construction, that is to say from point O, that is the center of this circle, we draw perpendicular on AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point M. By doing this construction, we get the quadrangle OMCB. Inside quadrangle OMCB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 angle, in total must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4 angle must be equal to 90 degrees in size. So in quadrangle OMCB, we have 4 angles, and therefore we can relate to quadrangle OMCB side angle. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle OMCB, side BC must be equal to the opposite side OM, but CB is 1, according to what is given as the equation, then therefore the opposite side OM must be also equal to 1 unit in its length. Likewise, according to the sum rule, in the same rectangle OMCB, side OB must be equal to the opposite side MC. But OB is x, therefore the opposite side MC must be also equal to x units in its length. What is the length of this missing answer at AM? From the drawing, it is very easy to see that AM in total equals to AC minus MC. Again, AM equals to AC minus MC. So AM in total equals to AC, that is 3, minus MC, that is x. So in total, AM equals to 3 minus x units in its length. In the next step, we join points O and A together by straight line. Point O is the center of this circle, point A is the point of the circle itself, therefore O is the radius of this circle, is equals to x. In the next step, implement the Pythagoras theorem on this green right line AOM. According to the Pythagoras theorem, in this right line AOM, AO squared, that is the square of the hypotenuse, equals to AM squared plus MO squared. And again, in this right green line AOM, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AM squared plus OM squared. AO equals to x, and therefore AO squared is x squared, and it is equals to AM OM squared. OM is 1, so OM squared is 1 squared, that is 1, plus OM squared, plus AM squared. AM is 3 minus x, therefore AM squared is 3 minus x squared. So in total, if you found out that according to the Pythagoras theorem, in this right line AOM, right hand side AOM, x squared equals to 3 minus x squared plus 1. So x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared, minus 2 times 3 times x, that is minus 6x plus 1. Here we have x squared on both sides of the equation, so x squared will get cancelled. After we cancel x squared, this side of the equation we left with nothing, that is to say 0. While on the other side of the equation we have 9 plus 1, that is 10, minus 6x. So in total, if you found out that 0 equals to 10 minus 6x. Here we added 6x to this equation, and finally found out that 6x equals to 10. Here we divided this equation by 2. 6x over 2 is 3x, 10 over 2 is 5. So in total, if you found out that 3x equals to 5, Here we divided the equation by 3 and find out that x equals to 5 thirds. X equals to 5 thirds. Our test is to find out the area of this circle. The area of the circle must be equal to pi times the radius of the circle squared. That is to say, it is pi x squared. X is the radius. So it is pi times x squared. X is 5 thirds, and therefore x squared must be equal to 5 thirds squared. So this is pi times 5 thirds squared. It is pi times 5 thirds squared. 5 thirds squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total, we found out that the area that we're looking for in this question, that is the area of this circle, it is equals to either 25 pi over 9 square root in size, or in terms of numbers, the area of this circle, in total, it is equals to 8.73 square root in size. Okay, thank you very much.